Hi there, Mix 2020. I'm Elliot Forbes. I'm an assistant professor at the University of Wisconsin-La Crosse and the faculty advisor on the presentation you're about to see. I just wanted to step in here really quick and thank you for watching our video. But I also wanted to introduce our presenter here. So I'm going to hand it over to Justin Severeid. He's an undergraduate here at the University of Wisconsin-La Crosse. He's studying our computer science with an embedded systems emphasis program, and he'll be one of the kind of first handful of graduates underneath that emphasis. So he's really good at this low-level system software development. I've talked to him recently, and he said that now that he's worked on this project, he dreams in regular expressions. So that's exciting to hear. So thanks again, and I'll hand it over to Justin.
Thank you for the introduction, Professor Forbes. Today we'll be talking about DuctTape, a high-level RISC-V assembler. First of all, what is DuctTape, or DT for short? DT is a programming language and assembler that targets the RISC-V instruction set. It differs from standard assembly and GNU tools by providing several syntactical constructs borrowed from higher level languages, such as while loops and if statements. Essentially, the result is a hybrid language that is part assembly and part high-level language. DT was also written using the tools Flex and Bison, so if you're familiar with those tools, the code base is really easy to wrap your head around. And the goal for this project was to create a useful tool for the early development of simulators, microkernels, and VMs. Because of the open source nature of RISC-V, there is an increasing number of hardware and software projects that target the RISC-V instruction set. Some of these tools include instruction set emulators, processor simulators, compilers, operating systems, and virtual machines. When developing tools of this nature, there requires a large amount of attention to low-level detail. DT can help developers write these programs that will exercise these low-level details while still providing some creature comforts of high-level languages. DT isn't designed to compete with these other tools, but rather to be complementary to the existing RISC-V tools. So you may be thinking, why can't you just use GCC to write these programs that exercise the low-level details? Well, GCC doesn't give the programmer enough control. So GCC doesn't allow the programmer to specify registers, specify memory locations, specify the type of instruction, or specify the order of instructions. You may be wondering, what is RISC-V? Well, RISC-V is a free and open instruction set based on the reduced instruction set philosophy. RISC-V is extensible, it's designed for a wide range of uses, and it's gaining industry and academic support quickly. DT implements a high-level assembler that targets RISC-V. In the past, there have been efforts to implement a high-level assembly. However, these past assemblers typically require assembler directives to provide some high-level language features. What sets DT apart from these other assemblers is that these high-level language features are native to DT. The figure towards the right shows the high-level organization of a DT program. So each DT program is composed of one or more mem blocks. The mem blocks are used to encompass 0 or more statements. Each mem block must be supplied an address which will serve as a starting address for any statements which will occupy memory in the output file. DT also allows for multiple mem blocks. Because of this, DT will also determine the size in bytes of each mem block and verify that no addresses overlap and that all starting addresses are correctly word aligned. The DT program can also be split into multiple files. By convention, these files are named with a .dt extension. There are currently no restrictions on the number of mem blocks for a program targeted for flat memory image output. However, for the ELF64 Linux executable, there are some restrictions. The program entry point must conform to the Linux ABI when using the ELF64 format. The statements that appear within a mem block can take several forms, some of them being comments, names, definitions, data values, assembly instructions, and high-level language constructs. So in DT, comments start with the pound symbol and can appear anywhere within a program. Also, to increase readability, labels can be defined for memory locations and registers. DT is globally scoped, so the labels defined in one DT file can also be used in another DT file without any issues. If you take a look at the code snippet below, you can see that we have a label count defined for the register X8, and that label is then used in the add-I instructions. These instructions are also within a mem block with the supplied address of hex 10,000. Data values. The programmer is free to hardcode any values to any memory location. DT supports this by providing several assembler directives to control the amount of memory and the format of the initial data values. The data values can be intermixed with instructions, but we leave it up to the discretion of the programmer to make sure that data values aren't executed as instructions. This table shows the supported directives and an example of the directive in use. It's pretty straightforward. You just have to write the directive and then write the data that you would like to place. Assembly instructions. The assembly instructions are specified by the usual syntax of RISC-V, which is specified in the RISC-V ISA. In general, this just means that the instructions are specified by an instruction mnemonic followed by register, immediate value, or labeled operands. However, the real strength of DT lies in its support for high-level language constructs, such as if statements or while loops or arithmetic operators. So these high-level language constructs can also be mixed with low-level assembly syntax, and the high-level constructs are then converted to a deterministic assembly output. And there's also support for high-level assignment and arithmetic operators. So DT supports several control flow constructs, such as if statements and while loops. These constructs, they take a register or a label pointing to a register. Here is a code snippet showing some of the constructs in use. There's an if statement, and towards the right is the accompanying assembly output. And there's also a while statement and the accompanying while statement assembly output. One instance that DT was used was for a hardware bug workaround. After a chip was sent off for fabrication, it was discovered that there was a hardware bug. Whenever a load instruction was queried, the cache would always respond with a hit. Fortunately, there was a workaround. We would simply have all loads prefetch cache blocks with the correct data. Unfortunately, this did affect the performance estimations, but the system could at least demonstrate functional correctness. If GCC was our only tool for creating executables, then it would be nearly impossible to guarantee that all the load instructions had their data prefetched. This is one of the prime use cases for DT. If you take a look, here's a snippet of the DT source code that was used to create this workaround. As you can see, we are using some high-level assignment constructs and some condition constructs as well. DT was validated in both hardware and software. DT was validated in hardware using the Hi5 Unleash board by Sci5, and DT was validated in software using RV8, a RISC-V simulator. Initially, during the development of DT, we used RV8 to test DT. However, after test cases were written, then those executables were moved onto the Hi5 Unleash board running a Linux environment. In the future, we'd like to add support for compressed RISC-V instructions, as well as support for struct-like data types, and support for additional output file formats. Currently, the only output file formats available are a flat memory space file that can be integrated into a processor or simulator, and the ELF64 format, which is suitable for executing RISC-V on a Linux development environment. Thank you for watching. If you have any questions or comment, please direct them to eforbes@uwlax.edu and severeid.justin@uwlax.edu. Thank you.